I'm very happy for this first seminar to have someone that a lot of you know very well, Forrest Agostinelli. Forrest did his PhD here, wrapping up last year, working with Professor Baldi. Before that, he received a bachelor's degree from Ohio State and a master's from the University of Michigan. This summer, Forrest has just joined the faculty of the University of South Carolina as an assistant professor in the computer science and engineering department. And in his thesis, Forrest did lots of really interesting work that was, kind of at the intersection of deep learning and reinforcement learning, as well as thinking about how these things apply to important scientific problems. And he's continuing that space, is going to tell us about some of this today. So without further ado, please go ahead, Forrest.
Thank you. Hi, everybody. It would have been great if I could have been there and seen you all in person and got a bit of the California weather again, but oh well. So today I'll be talking about combination puzzles, in specific, the Rubiks Cube and its relationship to problems in the natural sciences. So I'll talk in specific about problems in chemistry, but then I'll also talk about relationships to problems it has in mathematics, such as group theory, as well to problems in theorem proving, and as well as using this as a test bed for collaborative artificial intelligence. So before I start, I just want to thank all my collaborators, especially Pierre Baldi, my advisor, my PhD advisor, and also Professor Paolo Sassana-Corsi, who passed recently. And also want to thank Samir Singh, who's also here, and he was on the committee for my thesis defense. So in general, what I want to do with my research is to design these artificial intelligence methods to solve real-world problems, and then use problems encountered in the real world to inspire future research directions. So in this talk, I'll be taking you all through a little loop of this, and hopefully I can continue this loop throughout my career. So the first part, I'll just be talking about the DeepCube algorithm and how we are able to apply it to solve the Rubik's Cube with deep reinforcement learning and search. And then I'll talk about applications of DeepCube A to problems in organic chemistry. And then I'll talk about how problems in organic chemistry are helping us think of new problems that we can pursue. Then I'll talk about future work for not just the DeepCube A algorithm, but building off of the Rubik's Cube to investigate new areas of research. So creating a learning environment involving puzzles. There are a lot of advantages to working with puzzles, and I'll discuss those. And then I'll talk about how can we actually approach this problem if we were solving the Rubik's Cube in the real world. So there was some robot with some actuators, and you just gave it a scrambled cube, and you told it what you wanted it to look like, and then you just said go. So how could you actually get this done in the real world? And then I'll talk about generalizing the DeepCube A algorithm. Specifically, I'll talk about problems in theorem proving as well as chemical synthesis and how these are related to the Rubik's Cube. And so this is just how we can use DeepCube A for a much more general, to solve problems in a much more general sense. And then I'll talk about relationships to collaborative artificial intelligence. So for example, if I know how to solve the Rubik's Cube, then I can probably explain to you how to solve the Rubik's Cube. However, with the DeepCube A algorithm, it knows how to solve it, and it just takes a series of seemingly arbitrary steps and gives no explanation. So how can we instead work with artificial intelligence to take us from a place of knowing nothing about a problem to actually having an intuitive understanding of how to solve that problem? So as I said before in this loop, the first part, I'll be talking about designing these new artificial intelligence methods on this DeepCube A algorithm. I'll talk about the relationship to organic chemistry and then how this is inspiring future research directions. And first, I'll start with the DeepCube A algorithm. So the Rubik's Cube is a pathfinding problem. You want to get from some point A to another point B. And the point B is where all the colors on each side are the same. And this is encountered in a lot of different areas, including robotics and also including in organic chemistry. Say, for example, you want to design some molecule and you have some building blocks. And so you want to find a path from your building blocks to the molecule that you want to design. Another relationship between solving the Rubik's Cube exists in optimization. So say you have some optimization problem like you may encounter in protein structure prediction. You can calculate the free energy of a protein, and you want to find some configuration that minimizes this free energy. The difference is you don't actually know what that final configuration is. If you did, then you would be done, and you can just go right to that final configuration. So the problem is searching in this really high dimensional space to actually find a solution to this problem. And this is a similar problem encountered when solving the Rubik's Cube. We have this very high dimensional space, and we need to be able to search intelligently in this high dimensional space to find a solution. Another area where optimization is important is with circuit design. So you want to find some circuit that performs some task, but also minimizes the space it takes up, or also is more energy efficient. And this is also an optimization problem, similar to that of protein structure prediction. So why do we even care about the Rubik's Cube? Why do we even want to solve the Rubik's Cube? Well, first, as I mentioned before, it has a very large state space, 10 to the 19 possible configurations. On most computers, you won't be able to enumerate every possible state and find a solution that way. We also work with puzzles with larger state spaces than this. The largest we worked with was 10 to the 63 possible configurations. Also, we don't have any domain-specific knowledge. So we solve the Rubik's Cube as well as 6 other puzzles, and we do it with the same neural network each time. The only thing we're doing is we're swapping in and out which puzzle we're looking at. So this is learning to solve these puzzles in a domain-independent way. And we are really striving for this method of not relying too much on domain-specific information. But later on in the talk, I'll be talking about how we can actually learn some inter-domain information so that we can do transfer learning. Also, the Rubik's Cube is deeply rooted in group theory. So this can give us some information about what actually is our algorithm learning. For example, the Rubik's Cube has properties of symmetry. Is our algorithm actually learning properties of symmetry? Is it actually learning to take certain moves that are very common in group theory? And since we know a little bit about group theory, we can actually probe our algorithm to see what it's actually learning. And this, what we'll see in future slides, is a preliminary attempt to have an algorithm that is actually somewhat interpretable. So we have some preliminary attempts at this, and we hope to build off those results in the future. All right, so we investigated 7 total puzzles in this work. So the Rubik's Cube, we also investigated 4 different sliding tile puzzles. We see this 24 puzzle here. And so these are n by n puzzles. And the moves you can take in these puzzles are swapping this blank tile with any tile that is horizontal or vertically adjacent to it. And the goal is to get it to this final configuration shown at the bottom. And the 48 puzzle had a state space of 3 times 10 to the 62. So this was the largest state space that we investigated in this work. The next puzzle that we investigated was the lights out puzzle. So you could press any of these squares, and all of the squares adjacent to it would either flip on or off, and the square that you press would also flip on or off. So you can toggle these lights on or off, and the goal is to turn all the lights out. And the final puzzle we investigated was Sokoban. So in Sokoban, you are this green agent, and your goal is to push these boxes onto these red targets. Also, you can only, this environment is irreversible, so you can only push boxes, you can't pull them. The method that we use to, so as I was saying, the Rubik's Cube has this really large state space. So if you were to just start from some random configuration of the Rubik's Cube and using some randomly initialized algorithm that takes steps to try to solve the Rubik's Cube, it's very unlikely that you would actually stumble on the goal. So with reinforcement learning methods in smaller environments, this is feasible where you can actually stumble and get some reward and learn from that reward signal. But here we're dealing with the sparse reward problem, or what you could also call the uniform reward problem. So for every step you get a reward of -1, your goal is to maximize the reward over time. That means your goal is to solve the puzzle in the fewest number of steps possible. However, you're not gaining any information as you're taking steps because you're just always going to get a reward of -1. The only thing you actually know in this environment is what state is considered the terminal state, or what state is considered solved. And so the thing that's really kind of straightforward and simple to do is prioritize sweeping. So we can start from the goal and we can scramble the puzzle a couple times. Now, it would be pretty simple to learn how to solve these states that are really close to the goal. Now, we can also generate states by scrambling the puzzle even more times. And then we can bootstrap from the knowledge we learned from solving these simpler states to solving progressively harder states. And of course, we can solve it even more times. And so what we're doing is we're generating a set of states to train on whose difficulty ranges from easy to hard. And we're bootstrapping from the knowledge we acquire when solving easier states to learn how to solve progressively harder states. Just one caveat is with the Sakavan environment. As I mentioned before, it's irreversible. So we can't scramble it in the same way that we scrambled the Rubik's Cube. So what we would do is we would start from this goal state, and instead of pushing boxes, we would then pull boxes. And later on, I'll talk about ways that we can actually avoid having to do this. So as I was mentioning before, I'll talk about how can we actually solve the Rubik's Cube if we were working in a physical environment and we couldn't just start from the goal and work backwards. What can we do? And so I'll talk briefly about that. And we'll see that maybe we don't have to do this for all problems. Maybe there are some problems where we can actually still do something like this without explicitly building this backwards model of the environment. So as I mentioned before, these are the states that we're going to train on. Now we have these states, the difficulty ranges from easy to hard. What do we do after that? So this is a very basic algorithm in dynamic programming, and this is called approximate value iteration. And the intuition behind approximate value iteration is, okay, we can't store all states in a table. And usually in the value iteration algorithm, what you would do is you would store every state in a lookup table, and you would do value iteration until you converged after some point. However, there are too many states to do this, so we use an approximation architecture, in this case, a deep neural network. And the approximate value iteration algorithm works by through bootstrapping. So you're going to, given some state S, you're going to look at every possible action you can take, and you're going to look at what we're going to call the cost to go of every possible state. And the cost to go is the estimate of the number of moves it would take to get from some state to the goal state. So we're going to look at every possible move we can take, the cost it would take to make those moves, which is this G here, and the cost to go at the resulting state. And we can back this up by just looking at what's the action that we can take that's going to minimize the sum of the cost it takes to take that action, as well as the cost to go from the resulting state. And we're going to back that up, and that's going to be the target for that state. So initially, we're going to just start out by saying the cost to go for every state is 0. And this is going to provide a target for our deep neural network to learn from. And then after a while, we can update our deep neural network and learn from that target. And we can do this iteratively until we have a better cost to go function. So we have used approximate value iteration. We found a cost to go function. What happens if we just behave greedily with respect to this function? So we're at some state, we look at every possible action we can take, and we take the action that has the lowest cost to go. What happens in this case? So in this plot here, on the x-axis is the number of training iterations, and on the y-axis is the percent solved when behaving greedily with our cost to go function. And each one of these lines represents cubes that have been scrambled a certain number of times, between 1 and 30 times. So you see, for cubes scrambled up to 7 times, it solves all of them after a certain point 100% of the time. However, if you scramble them about up to 10 times, it only solves about 95% of them. 13 times, it only solves about 75% of them. And so as you scramble them more and more, it becomes less and less reliable, just behaving in this greedy fashion. So we're going to have to find a better algorithm for solving the Rubik's Cube. Well, this cost to go function can readily be used as a heuristic. So for all of you familiar with A-star search, we know one of the core parts of A-star search is your heuristic function. So this heuristic function is just estimating the cost that it's going to take to get from some state to the goal state. And what we're going to be doing is we're going to start from some starting node, and we're going to expand nodes according to some priority until we've selected the goal node for expansion. And the way we prioritize the nodes that we expand is this g of x plus h of x. So this h of x is the heuristic, which is just our cost to go function. And this g of x is the path cost. So what is the cost from starting at the state, the starting state x of s and going to state x? And so this f of x, what it's saying is it's summing together the cost it took to get from the starting node to the current node and the estimated cost that it's going to take to get from the current node to the goal node. And we're going to prioritize nodes that have the lowest cost so that we think are going to have the lowest cumulative path cost when we actually find a solution. Also, this A-star search typically expands one node at a time. However, we have this deep neural network that we're using as our heuristic function. And so we instead can expand many nodes at a time to take advantage of the parallelization provided by GPUs. We also can add a weight to our path cost so that we can pay more attention to our heuristic function if we think that it's beneficial to us. So in our experiments, and if you, this is generally called weighted A-star search, if you put less weight on the path cost and more weight on the heuristic function, you can find potentially, you'll be potentially more memory efficient and potentially execute the search faster for potentially shorter solution, for potentially, longer solutions. So solutions that take more steps, but you can save a lot of memory by doing this. And the architecture we used for every puzzle is this residual neural network. And for every puzzle except the 24 puzzle, this was exactly the same. For the 24 puzzle, we just added 2 more residual blocks, but it's still the same type of neural network. And what we did for every puzzle is we just had to change what the goal state was. We had to change the representation we gave to the neural network. And we had to code what moves you could take in this environment. However, the learning algorithm itself remained the same. So we actually use the same hyperparameters for everything when doing approximate value iteration. And we use slightly different hyperparameters for the weight when doing weighted A-star search. But overall, the algorithm was the same and the structure of the deep neural network remained the same. All right, so we were able to train a cost to go function using approximate value iteration. We saw that approximate value iteration was not 100% successful. And so we then used this cost to go function as a heuristic function in A-star search. And
can I ask a question?
Yes, go ahead.
I just want to clarify the neural network, or what you showed in the previous slides and these layers. is this what you do in order to generate the heuristic, or this is what you do? It has anything to do with the A-star search that you are doing?
Right, so this is what we use to generate the heuristic for A-star search.
Okay, so it's only the heuristic.
Yes.
Okay, thank you.
All right, so now let's put this all together and see how well it works. For the Rubik's Cube, we generated 1,000 test states by starting from the goal and scrambling the cube between 1,000 and 10,000 times. We did this for all the other puzzles, generating 500 test states by starting from the goal, also scrambling it between 1,000 and 10,000 times. We also, for some of the puzzles investigated here, not for all of them, we can use handcrafted shortest path solvers so that we can understand what, so that we can actually get the cost of a shortest path and compare our algorithm to a shortest path. So these handcrafted shortest path solvers, they often take advantage of certain symmetries in the puzzle and certain knowledge about group theory so that they can operate pretty quickly to find an optimal solution. But this isn't computationally possible for all the puzzles we investigated. All right, so here are the results. For the Rubik's Cube, we were able to find a shortest path 60% of the time. And for the ones that were not on a shortest path, I believe the overwhelming majority were actually only 2 moves away from a shortest path, and a couple of them were were 4 moves away from a shortest path. So they were 60% were a shortest path, and the rest were close to a shortest path. For the 15 puzzle, we were able to find a shortest path 99% of the time. For the 24 puzzle, we were able to do this 96% of the time. For Lights Out, we were able to do this 100% of the time. And we were able to do all of this on the order of seconds. All right, so we saw how we performed on these randomly generated states. But one might ask, how do you perform on the hardest states? So what are the hardest states? Well, these are the states whose shortest path is the maximum out of all the states in the state space. And we know these states for the Rubik's Cube and for the 15 puzzle. So for the Rubik's Cube, there are 3 states that are 26 moves away. And for the 15 puzzle, there are 17 states that are 80 moves away. And some Rubik's Cube nerds might say, oh, wait, but I thought what's colloquially referred to as God's number, the maximum of the minimum number of moves needed to solve the cube, I thought that number was 20. So if you're using the half-turn metric, this number is 20. That means every, you can turn aside 180 degrees and that counts as 1 move. We used a more restricted set of moves where every 90-degree turn counted as 1 move. So if you want to make a 180-degree turn, this is 2 moves. And this is known as the quarter turn metric. And we just used it because it was a subset. It was a simpler move set than the half-turn metric. So in there, that number is 26. Just wanted to explain just in case. I know I would have the same issue. All right. So for the Rubik's Cube, we were able to find a shortest path for all 3 of these hardest states. And for the 15 puzzle, we found a shortest path 17% of the time. However, we were on average 2.28 moves longer than a shortest path for the 15 puzzle. And then we also wanted to investigate what our deep neural network learned about group theory. So one thing we did is we looked at every triplet used to solve the Rubik's Cube. And we found that this A-B A inverse pattern happened a lot. Excuse me. An A-B A inverse pattern is when you take some move A, you take another move B, and then you reverse the original move A that you took. And so this may show up, you've probably heard about this if you have studied group theory, but this showed up, this accounted for 13% of all the triplets that DeepCube used. And then we also implemented, we also investigated symmetry in the Rubik's Cube. So the Rubik's Cube has 96 different ways it can be symmetric. And we investigated just what would happen if you flipped it along one axis. So you took these mirrored states and you solved these mirrored states. And what we saw is that DeepCube found a symmetric solution to symmetric states 58% of the time. And so a symmetric solution means that if you solve one puzzle and then you just mirror all those solutions, mirror every step, then you can solve the mirrored version of that state with the mirrored version of those steps. And below is an example of it doing this. So these two states here are mirrors of each other. And where you can see that it's using these mirrored steps. And you can also see that it's using these conjugate patterns, this A, B, A inverse. Now, I'll talk about this in further slides, but we had to actually, poke the network, and we had to actually know something about group theory before we were able to even investigate whether it had learned something about group theory. So it would be nice in the future if it could actually tell us these things without us having to explicitly ask it about it. And so here is a demonstration. I just checked the server, it should be up, but here's a video of it working. We changed some of the hyperparameters on A* search so that it can solve it faster. And so on the web server, it solves it in a second. So if you scramble it and then press solve, it should come back with a solution in a second. And this got picked up, because it's like a pop culture reference. It got picked up by some news sources like BBC and things like that. And I was, constantly talking about, oh, it can find the shortest path. This has implications for doing things efficiently, for not wasting resources. It has implications for the environment. We want to behave efficiently and not waste resources. And then someone asked me how fast did it work? And I hadn't really thought about it, but I was just like, oh, if you want to do it in a second, then you could do it in a second if you wanted. And then the next thing I knew, there was all these news articles like AI solves the Rubik's Cube in 1 second. I was like, whoa, where did this come from? So it was kind of interesting because I learned you couldn't dictate to other people what they should find interesting. So yeah, that was just a funny story. All right. Okay, so we talked about these puzzles that have these really large state spaces. We can't possibly enumerate all these puzzles. However, so we want to be able to solve these in an intelligent way, and we want to come up with an algorithm that's somewhat domain independent. And so we saw we were able to solve 7 of these puzzles, finding a shortest path in the majority of cases. Now, how can we apply what we've learned when solving the Rubik's Cube to real world problems? And so I'll start talking about problems in organic chemistry in this section of the talk. All right, so say I have some chemical reaction. I have some set of products and some set of reactants and some products. And I want to know what were the reaction mechanisms. So what were the smaller steps that actually led to this reaction? So this is possible for domain experts to figure out. They'll have to have a good amount of domain knowledge and write out by hand how this reaction might have happened. However, we're looking for a way to automatically understand how this reaction could have happened. And this has relations to problems in drug design as well as drug toxicity. Say, for example, you have some drug to treat some disease, and you want to know if there could be a series of chemical reactions that could actually lead to something toxic. So this is a pathfinding problem. You have your starting state, whatever the configuration of this chemical compound is, and you have this end state where there's something toxic. Now, you don't know if it exists or not. So this is a slightly different problem. It's like a needle in a haystack where you're not even sure if the needle is there. Now, for this organic chemistry, we can represent molecules using graphs. So we used a graph convolutional neural network. Each node in this graph was an atom, and the edges were bonds. And we used this graph neural network to predict the cost to go. The actions it could take in this environment was to make and break bonds, as well as to donate electrons. So here's just some preliminary results when applying DeepCube to this algorithm. I don't expect people to understand what's going on with these Lewis structures, but I'm just going to play a video that shows it using these actions that we've defined to find a path from this starting state to this goal state. So here's it taking these actions. In about 6, 7 actions, it's found this goal state. So let's look at this a bit deeper. We showed this to our collaborator who is in chemistry. And one thing that he said was that the actions that this takes are the correct actions. However, they're out of order. They wouldn't happen in that order. So why is this happening? And this takes me to the next part where these real world problems are actually inspiring future research directions. Well, not all chemical reactions are equally plausible. So if we're looking at what steps a reaction might have taken, not every step is going to be equally plausible. So we can incorporate this in our search algorithm based by making reactions that are less plausible, more costly, and reactions that are more plausible, less costly. So if we want to find a minimum cost path, that would be the same as finding a path that is the most plausible to go from some set of reactants to some set of products. Now, the A* search algorithm has a unique property. If the heuristic function is admissible, then A* search is guaranteed to find a minimum cost path. It's guaranteed to find the shortest path or a minimum cost path. Now, what does admissible mean? So admissible means it does not overestimate the cost of a shortest path. So in these two plots, you have on the x-axis the cost of a shortest path, and on the y-axis, you have the heuristic function output. And this is for the 15 puzzle. So what DeepCube learns is something that is sometimes admissible, sometimes inadmissible. So sometimes it does not overestimate, and sometimes it does. What we would like is to modify this so that it never overestimates the cost of a shortest path. And we have some preliminary work on this, and we can show that for the 15 and 24 puzzle, that using this method, we can find the shortest path 100% of the time. And like I was saying before, these guarantees, trying to guarantee with high probability that you're going to find the shortest path, could have significant implications, not just in the chemistry world, but also for real world consumption. If you're doing manufacturing, if you're trying to run a hospital, you're trying to coordinate a lockdown, you want to make sure that you are reducing the amount of unnecessary waste. Another issue that we had with this chemistry data is that we would follow the same procedure we did for the Rubiks Cube. We start from the products, and then we randomly take action so that we can generate states whose difficulty ranges from easy to hard. Now, the issue with this is most of the states we generate are actually completely irrelevant to the problem at hand. We actually don't care about most of the states in this state space. We only care about states that start at this given starting state and could have possibly made it to this end state. So to give a sense of what I'm talking about, take this really simplified 2D environment. We have this goal state on the left, and we have this start state on the right. And each of these red points are what DeepCube would generate for training states if you just start at this goal state and randomly take actions. And you see that a shortest path is just directly from the start state to this goal state. So 2 problems. One is most of these states are not relevant. And 2, many of the states that are relevant are completely unexplored. So what we've been looking at is this bidirectional search. So instead of generating states randomly by starting at the goal state, you can generate states by starting at the goal state and actually trying to find a path from the goal state to the start state. And so we had some preliminary experiments in this really simplified environment, and we saw that the training states eventually were all concentrated around the most relevant, this most relevant shortest path. All right, so where can we go from here? So I talked about Deep Cube A, how we can solve these puzzles in a domain-independent fashion, how they can be applied to problems in organic chemistry, as well as how problems in organic chemistry are motivating future research directions. So what are we looking at in terms of future work in a broader sense? So one thing we're trying to build is this puzzle learning environment. So currently DeepCube, it can solve some of these larger Rubik's Cubes, for example, the 4x4x4 Rubik's Cubes, or these Rubik's Cubes in higher dimensions like 2x2x2x2. However, it's very inefficient. And so some states it may be able to solve in a reasonable amount of times, but other states it just may take too much time or too much memory. So there's a lot of work that still has to be done. And this is a picture of the large variety of combination puzzles that are out there. And one thing that I noticed is after I learned how to solve the Rubik's Cube, if you gave me a different combination puzzle, what I learned from solving the Rubik's Cube would translate over to learning how to solve these other puzzles. And so we want to create an environment of many different combination puzzles and try to see how we can use these puzzles to do things such as transfer learning. If I learn how to solve the Rubik's Cube and you give me a Scube or you give me a Megaminx or something like that, it should be easier for me to solve it. We also want to look at what we can learn about with group theory by solving these puzzles. We also want to look at interpretability. So solving these puzzles is nice, but we should be able to learn something about these puzzles, learn something about the algorithms by applying artificial intelligence algorithms. And then what I'll talk about in the last slide is this collaboration between humans and artificial intelligence. So what I mentioned at the beginning of the talk is, say you had some robot with some actuators that could move the Rubik's Cube. And you could give it a scrambled cube, say the one you see here, and you could tell it what a solved cube looked like. However, that was all you could give it. What can you do to actually solve this puzzle? So you see the DeepCube algorithm is not going to apply in this situation because we cannot start from the goal and work backwards. We're not given a model of the environment. We're not given a solved cube. We're just given some scrambled cube. So are we able to actually, is DeepCube actually going to work in this environment, or is there some way we can modify it? So there's some preliminary work that we're doing that shows we can use a method called hindsight experience replay. I think some of you may be familiar with it, but we can use this method to actually start from some given start state, but learn a cost to go function that generalizes not just over start states, but also generalizes over goal states. So we can find a path, not just from any state to the goal state, but from any state to any state. So if we wanted to go from this puzzle, this configuration here on the left, and go to this configuration here on the right, we could do it. Now, the next step we're working on is integrating a learned model with A-star search. So through fiddling around with this puzzle, the AI agent should learn something about how the puzzle moves such that it could actually use that to search. And so you can then give it a puzzle and it would be able to search for the best path to solve this puzzle. And then without you telling it what the model is, just by interacting with this cube and actually find a solution. So that's the goal. Also, I want to look at generalizing to DeepCube to different problems. For example, we were talking about robot navigation. This could be in object manipulation or object assembly. And then also to optimization problems. We've been working with these really large state spaces. How can we also tackle really large state spaces in problems such as protein structure prediction and circuit design? In particular, I'm interested in generalizing DeepCube to problems in theorem proving as well as chemical synthesis. So theorem proving and chemical synthesis are actually very similar. So the way a lot of theorem provers work is they start from what they want to prove, and they work backwards to some axioms, so something that has already been proved. Similarly, with chemical synthesis, what people will do is what's known as retrosynthesis. They'll start from some target molecule, and then they'll work backwards to some available building blocks that they can immediately access to actually build this target molecule. So this can also be posed as a pathfinding problem. You want to find some path from your building blocks, whether they be chemical building blocks or axioms, to some goal state, whether this is a target molecule or some theorem that you want to prove. And so the connection between DeepCube and theorem proving as well as chemical synthesis is there. And so I'm looking to explore more of this area in the future. Also, if you solve the Rubik's Cube or your friend solved the Rubik's Cube, they can go and teach somebody else. And then that other person can learn how to solve the Rubik's Cube, and they can be the center of attention at a party or something like that. It would be great if we could collaborate with AI to find solutions to problems. So not just for being the life of the party, but say for planning something that is really complicated, for example, a lockdown. Now, if we just use some algorithm that spits out some seemingly arbitrary steps and gives no explanation for it, even if this may work on paper, maybe on paper this is the most efficient way you could possibly do a lockdown, humans are not going to trust it. And so therefore, they would rather go with something that they can intuitively understand. And so we need to be able to trust these AI algorithms when they're actually showing us how to solve a problem. So with collaborative AI, what I'm trying to do, starting from the Rubik's Cube, is first be able to give some high-level intuition of how you think the Rubik's Cube might be solved. So this doesn't have to be correct. Maybe it's an infeasible plan, but there should be a way for the algorithm to go through your plan step by step and then be able to diagnose which parts of your plan are an issue. So maybe it's having a really hard time from getting from step 3 to step 4. It could give some feedback and saying, step 3 to step 4 is just too difficult. I think there's something wrong with your plan. And maybe give suggestions about what might be wrong. Additionally, you may come up with a feasible plan that's you can actually execute, but there may be some inefficiencies. And you should be able to get feedback about where these inefficiencies are and iteratively improve your plan. So in this case, you can get a very high-level overview of what this algorithm is doing by collaborating with this AI. And so you don't have to be right on the first attempt, and you don't have to be the most efficient on the first attempt, but you're going to iteratively interact in a human-in-the-loop sort of fashion to solve these problems. And this can work. This can give us a way to solve these more complicated puzzles, and in general, just more complicated problems, because maybe on its own, these artificial intelligence algorithms may not be able to solve maybe some really large Rubik's Cube, may not be able to solve what's the best way to do a lockdown. But by having a human in the loop, we can be able to come up with good solutions to these problems together. Also, once you have a high-level plan, the low-level steps should also be interpretable to a human. So when solving the Rubik's Cube, people often have this strategy of, you get the cross on top first, and then you get these individual parts next, and then you get some edge pieces in the second layer, and so on and so forth. So this is a high-level plan someone will describe, but the low-level steps to get there are also something that we can intuitively understand so that we can put this all together and solve the problem. So when solving the Rubik's Cube, people don't enumerate every possible low-level sequence of low-level actions to get from step to step. Instead, we use some high-level concepts, such as giving names to the specific sections of the Rubik's Cube, naming commonly occurring sequences, as well as naming color patterns, so that we can categorize different low-level sequences of actions. Also, it should be able to, maybe you give it a set of low-level sequences of actions that you're comfortable with, but it should be able to propose new concepts to the user to produce even better plans. And then this is also related to education and knowledge discovery. So education in the sense that maybe we can collaborate with artificial intelligence to better teach kids when they're learning in class. Maybe we can collaborate with artificial intelligence to learn things that we actually never knew before. So there may be some problem that people couldn't solve, some theorem that people couldn't solve before, but maybe by collaborating with artificial intelligence, maybe you have some semblance of how this theorem could be solved, and you iteratively collaborate, iterate on this algorithm with your artificial intelligence collaborator, and actually be able to, say, prove a new theorem or design a new drug. All right, so that's the end of my talk. Thank you all very much. Any questions?
Okay, thank you, Forrest. So if anyone has questions, you may either use the chat window to type it, or you should also, I think we have a small enough group here, if you'd like to just unmute yourself and ask it, you can go ahead.
Yes, Professor Decker.
Oh, okay. I don't see the whole screen, so I didn't know that you are talking to me. Yeah, I have, I would say, a comment and two questions. One question is, can you give us an idea about how much time does it take for this whole process of learning, let's say the Rubik's Cube or another puzzle, how much time it takes and what is involved? That's one question. Another question is, can you say a little bit more about how you generate this more admissible heuristic that you mentioned? So you mentioned that at some point you recognize that the heuristics that you're generating are not admissible, but admissibility is desired to guarantee optimality. And the third is just a comment. There is I'm sure you're familiar with, all the work on search. So search is a huge area and people are working on it for many, many years. And in particular, recently, there is some breakthrough in bidirectional search in the theoretical search community. So I don't know if to what extent it's relevant, but this is coming from University of Alberta for Rob Holty. And I don't know to what extent it's relevant, but I thought I would mention that. So that's it.
Yes, that is very relevant. Thank you. And for your question about how long it takes for each puzzle, it took about a day and a half. And we used about 8 GPUs. So it was pretty expensive process for each puzzle. It takes a day and a half. So this is one reason why I'm interested in this transfer learning. But then another reason why I'm interested in this collaborative learning. So if instead of trying to find any general solution from any state to the goal, you can give it a sense of these high-level steps it needs to accomplish, then you're significantly reducing the search space, because you're only looking for paths from step 1 to step 2, then step 2 to step 3. And what would be great is if you could be able to do this even on a laptop due to the significantly reduced space of combinations that are under consideration. So yeah, so that's what I had to say about the time. And then for your second question about, so I always forget when people ask me 2 questions, I always forget the second question. Sorry, can you repeat it?
So how do you generate, you make it admissible?
Right. So we were first starting with this proof. I'm sure somebody else proved it before, but I couldn't find it anywhere, where if you're doing A-star search and you have not yet found a path to the goal, if your heuristic is admissible, then in the closed set, the state that has the highest cost function, I believe it was the highest, is a lower bound.
The smallest, not the highest.
The smallest? Okay, the smallest cost function in your closed set. I believe, I have to look over the proof again, and I'll send it to you because I really want your opinion on this.
Yeah, I think it's always you improve the lower bounds as you do search. And when you stop, you have a better lower bound on the optimal solution.
Exactly. Yes.
So you are saying, but your search is not starting from an admissible heuristic. So this is only when you start with admissible heuristic.
Exactly. So this is the caveat. So we can start with a heuristic of 0 everywhere. And then we can use this to adjust our current heuristic function, but this will only produce a semi-admissible heuristic. So now the issue becomes, can you have some bounds on how often this is going to be admissible, and then relate that to how often you're going to find the shortest path? So that's the issue we're working with now, because we have this big function approximator. It's hard to analyze how often this is going to be, but maybe empirically we can find some bounds. Thank you.
Okay, thank you. Are there other questions before us?
It's Eric. I have a question. And you can see me ask it. Is there any advantage to be had by trying to learn a representation that makes hierarchical representations of the paths doable, so that you try to decompose a long solution path, such as might happen in a theorem, into big steps that each require lots of little steps?
Yes, that's a very good point, because we were talking about this with Stephen, Alex, and Roy. And so the idea we were discussing was, if you could project this state space into some latent space where the distance between points actually corresponded to the distance in terms of the cost to go, then if you wanted to get from one starting state to this goal state, then you could try to look for a point that is actually somewhere in the middle in terms of the distance between the start state and this point, and the distance between this point and the goal state, and then break this down recursively. So this is something that we've been looking at.
In mathematics, for example, one way I think mathematicians do that is by analogy with previously solved problems, and they see what their big steps were. And try to make a mapping from the old solved problem to the old solution of an old problem to the new solution of a superficially similar looking problem where the details are going to be different.
Right.
So if there's some way to bring new representations, maybe it's the latent space, maybe it's previous problems, and maybe it's both, then that might help.
Okay. Thank you. Yeah, that's a good point. Thank you.
Are there other questions?
Pierre is asking Justin or Khabib for the upcoming UFC fight. I'll have to pick Justin, Pierre. I know it's kind of crazy, but I think Justin's going to win. Sorry. Any other questions related to the talk?
So I have some. It seems like there's, in the approach you took, right, there's a real little bit of an art to getting the right data, right? I mean, because you have this enormous state space. It doesn't matter how much data you take, you'll sample it in a small part. And you had some kind of ideas, but it seems like a little bit of the magic in what you were doing is sampling the state space in a way such that you could learn an approximate value function that was useful for something. And I guess my question is like, how general purpose do you think the ways in which you're doing this now are, and like what's the path forward in that on that issue?
Yeah, so glad you asked that. So you're right. The way we're doing it was kind of serendipitous, that you can just start from this goal state and just scramble it randomly. But if you go to a different problem, such as Towers of Hanoi, this actually doesn't work because most randomly chosen actions will only get you a couple moves away from the goal state, just by the way this problem is set up. You can't put a bigger one on top of a smaller one. And so you never get really far from the goal state. So what I think is the solution to this is some notion of curiosity. So there's a lot of research on this artificial curiosity. For example, if you can't predict what's going to happen next, you can think of this as being curious to the agent. Or if your prediction of the cost to go seems to be really off, then you can also think of this as being curious. So you want to use some artificial curiosity to generate these states instead of doing it randomly. So you're actually looking for states that you're really unsure about, or that you have a hard time predicting what happens next.
Okay, thank you.
Thank you.
Any final questions? Okay, well, I'm sorry we can't all give you a loud round of applause, but thank you for a great talk,
Thank you.
for joining us remotely.
Thank you for having me. Really appreciate it.
Thank you everyone for signing on. We have lots of more great talks coming this fall, so please continue to connect with us. Thanks.
Bye, everybody.